Welcome, everyone. I'm excited to announce the next talk, Breaking NBAD and UEBA Detection by Charles Herring. Before I hand the mic over to Charles, let me run through a few housekeeping items. You can use the chat window to the right of the screen to ask questions throughout the talk, and we'll take the last 3 to 5 minutes for questions and answers session, maybe even earlier. At that time, we'll read through a few of the questions to the speaker. We BSidesNoVA also encourage everyone to stop by the sponsors area, which can be found in the Expo channel of this platform. If you visit a sponsor page, they should have resources and people available to chat about job opportunities. There is an open invite happy hour for those with a BSidesNoVA ticket at Punch Bowl in Arlington tonight, Saturday, from 6 to 9 p.m. The address is 4238 Wilson Boulevard, Suite 1180, Arlington, Virginia, 22203, if you really need the zip code. Now, I'm handing it off to Charles.
Hey, thanks, appreciate it, Brian. Feel free to drop any questions in chat as we go along. I did drop in a couple of links that I'll be using throughout the talk. Feel free to bring those up if I get too dry for you, but let's dig into it. So my last, what just happened? PowerPoint just died. That's a new thing. Sorry. Another little great start there. There we go. There we go. All right. So a little bit about me. Started my career in cybersecurity just after 9/11 at the Naval Postgraduate School. It's detailed there to spin up the network security group. Also worked with InfoWorld magazine in the test center testing security products up until the test center shut down in 2008. Left active duty in 2005. Did some consulting work with DoD, State Department around sharing cybersecurity information, how to operationalize it, that type of thing. I went to work for in the commercial space with Landcope, which is a network behavioral anomaly detection tool that I did some research with back in, at the Naval Postgraduate School. That company was acquired by Cisco and spun up WITFU in 2016, where we study what I call the 7 unstable conversations of cybersecurity operations. We're going to spend most of our time today on the first one, which is investigators needing to understand what their data is telling them. So we're going to break the talk down into a few different categories. First, we're just going to go over sort of how NBAD and UBA works in general. We're going to talk through data poisoning, how to prevent poisoning through non-repudiation and other protection mechanisms. We'll go through the attack scenarios and attack techniques to do the poisoning, and then we'll roll into some Q&A. So before I go too far, I'm going to kick off a script here that we'll dig into later. It's the script that's up on Pastebin, but it's going to take about 5 minutes to run to generate some nonsense messages. So I'll kick that off. So we talk through some concepts. So Dr. Dorothy Denning at the Naval War College in 1986, a long time ago now, wrote a paper called Intrusion Detection Expert Systems, and it defines the ways that we detect bad things happening. How do we do that in cybersecurity? And really, while marketing terms have changed and products have changed and all that stuff, the basic science behind it's pretty much been the same since Dr. Denning wrote it. But signature-based detection is when we inspect an object, a file, a packet, a communication. There's some object that we're looking at, and we notice there's something known bad about it. A file with specific hash, packet with specific markers, those types of things. You're looking at the object. And so signature-based detection, really cool. We know what it is. We have CVEs and other types of documentation associated with it. We tend to know what to do with it, how to block it, how to remediate it, how to protect against it. So intrusion prevention systems work really well in that space. Antivirus, EDR, content filters are all technologies that live largely in signature detection. Behavioral detection is when we look at not the object, but the subject. So what does the computer do after it eats the bad thing? Things like currently ransomware, we start seeing cryptographic key encryption happening across the disk, or a machine being used to send out spam, or a machine scanning the network. So these known bad behaviors, we might not know what the exploit was, but we know what the outcome is, that there's a number of things that computers in general shouldn't be doing. They're nefarious or suspicious behaviors. So technologies that use sandbox, malware sandboxing is a great way of, you drop the malware in there, you watch what the system does after it eats the file or executes the file, you detonate it, and you see what happens. If the behavior is a known bad behavior, you know that the file or the packet or whatever triggered that bad behavior is also bad. Network behavioral anomaly detection and UBA look for these bad behaviors in bad on the network, UBA sort of at a higher level. Host-based intrusion prevention systems are monitoring for known bad behaviors like reading the entire address book or sending spam, scanning the disk, doing encryption for extortion via ransomware, that type of thing. And of course, SIMs live in that space as well. And anomaly detection is still looking at behaviors, but it's not looking for known bad behaviors. It's looking at really whitelisting or baselining normal behavior and alerting when there's a deviation from normal. So there's really not the implication that something bad is happening. It's just a non-classified or abnormal behavior. And so the way that these things line up is anomaly-based detection helps us create new behavioral checks. We have some new anomaly like, hey, if we see these behaviors occurring, this behavior is something to look for. It's a new type of buffer overflow or a new type of scan or DGAs or one of the domain generation algorithms or something that we've realized are generally associated with more modern malware. So that was detected through anomaly detection because why are we communicating with geographically anomalous locations? We never talked to Russia. Now we're talking to Russia or some other locale. So anomaly-based detection creates new behavioral checks. Behavioral checks create new signatures. And signature-based detection really good for known exploits, very low cost of deployment, high fidelity in blocking, really good for known exploits. O-day, zero-day exploits, best caught with behavioral. So you might not know the payload, but you know it's the same old thing. They're trying to steal our money, trying to steal our data, trying to extort our information, trying to bring down services. So the behaviors tell us that something's going on, even though we don't know the exploit. And of course, when you have humans involved, there's really not payload, and you're able to have time and work at the speed of humans instead of the speed of computers. Credential abuse, whether it's, the credentials are stolen or the person is compromised, an insider threat, anomaly detection tends to be really the only way to catch those types of things. So when we talk about baselines, there's a few things to understand. If you're doing anomaly detection, you have to have a baseline. You have to establish normal, what the purpose of the baseline is. So one thing to look at is, do we baseline each entity? Do we have a baseline per computer, per user, per relationship, computer to computer, computer to user? Or do we look at it at a set level? So wireless machines to email servers, email servers to DNS servers. And so, to start baselining these sets, these members of entities. It takes time to build baselines, and not all time is the same. Humans interact with machines, and we tend to sleep. We tend to go to the bar, tend to go on vacation. We have different buying cycles. Prime Day is coming up, so we've got all these different things in the way that humans interact with each other that are not consistent. So that means if you're building a baseline, you need to build baselines that take that into account. Which generally means it takes a long time to make a good baseline. So what are you baselining? You have to have a metric or group of metrics that you're going to build it around. So supervised machine learning, we just pick things that we're going to baseline. How many bytes are consumed by this machine, or this group of machines? How many bytes are exhausted or sent out of the network from these machines? What time of day is it used? All these different things. So you basically pick a certain number of variables, you assign them to sets, and then you just build those baselines over time by monitoring the telemetry coming in on it. Unsupervised machine learning would just be building baselines upon every possible variable and every combination of variables. So you might say the type of services from these types of machines on these types of days with these protocols, or whatever that you want to build, and you look for building sort of these nebulous or permutations and permeations of baselines across every possible variable site would be unsupervised machine learning for the purpose of building baselines. Network behavioral anomaly detection really came around 2002 or so is when we started doing that as people, and it works off of meta. So a really cool thing about NBAD is you don't need to have a ton of data to make it work, not volumetrically a ton. NetFlow is layer 4 and below type of data. It's telling you who talked to who, how many bytes were exchanged, what were the TCP flags that were involved in those conversations. And it's just a record of a network conversation. So you can monitor what's going in and out of the network, but also more importantly, you can baseline what's happening internally inside of a segment, even with some of the newer technologies, or segment to segment across different locations or different areas inside of a network. Because baselines are built off of numbers, the metrics, the packets, the bytes, the connection counts, the relationships, virtually all that data is in NetFlow. And when I say NetFlow, it can be NetFlow v5, v7, v9, it can be IPFix, JFlow, CFlowD. There's a lot of different flavors. Generally coming off of routers and switches, generating that, or firewalls also do it. Visibility fabric from manufacturers like Gigamon are shaping traffic and create application metadata from those records, and that can be shipped in either IPFix or in Syslog using generally common event format. So it's just meta, just counting things that are going on, and are able to deal with that. And generally, because it's built on NBAD's built on NetFlow, it's sometimes grouped into NetFlow tools list of common things that do NetFlow. So when you're looking for building baselines, sort of the common ones are service traffic threshold anomalies. So you look at, okay, from wireless to our email servers, how much email traffic happens, how much SSH traffic happens, how much web traffic happens, those types of things. So you build baselines on groups, sets to sets, and the types of services that they are using, and how many bytes, how many connections, how many packets are exchanged, and you build baselines on that. And so if there's a deviation from that, you can alarm on it. Service type anomaly is pretty much the same thing. If a host is on the network and it only consumes web and email services, and all of a sudden it decides it's going to get into Tor or something else, that's a service. That's a net new service anomaly. You inventory all of the services. Geographic traffic. So if you are doing all your business with North America, all the traffic or a large portion of traffic is going to North America, then all of a sudden you're seeing it going to different geographic locations. That's a geographic anomaly, that what's baselined geographically is changing. Data hoarding or data staging is a really important one in data exfil evolution. So you count how many bytes each individual entity is collecting from internal sources, how much data is being moved from the servers to this particular client or group of clients, and so that you can detect data staging. So if it only consumes 500 megs a day, and then on a new day we get 2 terabytes of data collected from the network, that's a huge anomaly, which tends to indicate normally somebody's getting ready to quit. They're taking some records with them. Data disclosure is very similar. It's a client or group of clients that normally send, again, 500 megs out of the network to external sources. And today it's much higher. It's volumetrically higher than that. So you can alert on data disclosure, data exfiltration in those cases. Didn't list it here, but you can also look at beacons. If you start seeing regular connections that are occurring, they tend to indicate a C2 command and control. Can also be detected that way. So with in cybersecurity operations, when we first started doing it, those of us who've been doing it for a while, we started at the signal level. We'd get an alert, an alarm, an event that would come in, and we had an alarm table, and we'd try to work our way through that never-ending alarm table and investigate at that level. That was obviously too much. That was not sustainable. Didn't have enough context. Way too much volume. Then we started moving to computer-based or host-based investigation. So we would map all the alerts to the host that they're alerting against, and you would have things like most alarming host, and you would investigate the host and look at the alerts that are associated with the host, which gave you some level of consolidation. Sort of the next layer we went to in detection was mapping the user. Which users are associated with which machines, and then which events are mapped to those machines. And so you have sort of these relationships that bring human credentials into play, and you're able to do user-based investigations. And so when we talk about user and entity behavioral analysis, we're talking about not really looking at the alarm level. we're looking at the characteristics of the object, or as we would call it today, graph theory, right? We're looking at the graph relationship, the nodes and the edges, how they interact with each other, and how things change. And we do alert on known bad behaviors and anomalous behaviors lists you can pull up there on things that currently do this. Some common user anomalies are magic carpet. It's a really common one, that if a user logs in Cleveland and a few minutes later logs in from Tehran, it's not physically possible, given the current state of transportation, for him to get from Cleveland to Tehran that fast. So that's a magic carpet login. And so you look at that type of thing. You're maintaining state on user Cleveland, user somewhere else. And then when you look at those things together, those entities compared to each other tell you you have a magic carpet type of attack. Other thing to look at is baselining. When do people log in? If someone always logs in from 9 to 5, then all of a sudden we see a 2 a.m. login, that's a reason for concern. That's a baseline against TOD, or time of day anomaly. Host access. If the user normally logs in from his workstation, that's the only place that he or she logs in from. And all of a sudden now there's a direct login to a critical server. That's a host anomaly. That credential is not normally associated with that host. Same thing with data access. If a user's only hit an email and the HR application, and now all of a sudden the user is accessing data like source code that they would normally not do, that would be a data access anomaly. Same thing's true with service. If someone's never used, if a sales guy all of a sudden decides that they're going to start using SSH or something along those lines, like that doesn't seem like something that guy would do, that person would do. So that's all the background on how that stuff works. Let's talk about how to break it. So a few things I want to talk about. The types of data poisoning we have is what I call mass implication, which is my favorite one. I'll demo that to you. But essentially what that means is I'm going to do something bad, but I'm going to make it look like everybody else is doing it. And so when the investigators are trying to find me, they're going to have to go through all these ghosts, all these fake attackers that really weren't attacking to find me. Second thing we're looking at is baseline boiling. Since anomaly-based detection is based on baselines, what if we just break the baselines? What if we make the baselines so big that they can't be violated? I'll talk about how to do that. Also look at attack masking. So how to do an attack and then make it look like you didn't do the attack. A couple of methods we're going to look at is log spoofing. Log spoofing is when we generate a lie, a believable lie for something to consume, and process and make decisions based upon the lie. The second is where we're going to create a lie. We're going to create an artificial behavior and have something else generate the lie, the network switch or something else. We're going to look at doing that inside of a machine VM container, and also getting network devices such as switches, access switches, to do the lies for us. So this is what it looks like. So if this is the attack I'm doing, if I'm scanning the network, I've got a command and control channel back here, data staging, data exfiltration, here's the malware. If this is what's going on, and for poisoning data, we want one of two outcomes. If this is what really happened, we either want to make it all invisible, that's masking, and so there's nothing to investigate, or we want to do mass implication. So where you had clarity on what was happening here, now it looks like everybody's guilty of everything all the time, and it makes it virtually impossible to do an investigation. So these are sort of the two outcomes of what we're going to do to poison the data. Do want to talk about a little bit of protection. I'll end on this note as well later. Just to recap it, really important. Authenticating your sources are critical. For a long time, we've treated cybersecurity operations like an extension of IT, and it really has nothing to do with IT. It has everything to do with law enforcement. We're really extending investigations that are about detecting crime, responding to crime, and whether that's a civil matter such as violating corporate policy, or it's a legitimate, crime, felony. So we need to treat data not as data or as logs or as signals, but we need to treat them as evidence, which means we need to be very careful in how we collect them, how we store them. We need to handle chain of custody. And a big part of that is authentication, doing client-based authentication from the sending source. So having a public key infrastructure that issues client certificates to the firewalls, to the log servers, so that everything's being transmitted over client authenticated TLS is the most bulletproof way of keeping that of protecting the evidence. Of course, there's a ton of problems with that. RFC 5101 defines IP fix and it makes room for TLS, but I can tell you I have looked far and wide and I have not seen any solution that ships IP fix, over TCP, much less TLS. So that's really more of a hypothetical scenario when you're dealing with NetFlow, IP fix, and that type of thing. It's expensive. It's computationally much more expensive to do TCP, TLS handshake, key exchange, certificate revocation checking. So you got to have beefier boxes to do it. It means you're spending more money to encrypt, not just encrypt the channel, but also authenticate the channel. And then you do run into potentials of denial of service by reflection attacks. But again, that is, if you can engineer that where you can put client authenticated exchange and logging, that is so important. It's so critical to closing it off anywhere you can do that. And when you're working with different vendors, manufacturers, it's a good feature to make important to them. Where you want to do IP spoofing protection. UDP, you can mangle the header and say that you're whatever IP you want to say you are. So you can make your sending IP address in a UDP packet the firewall's IP address, and that makes it very hard for incident responders to figure out what real logs came from the firewall and which ones that Charles made up, right? So IP spoof protection is available in some versions of some routers and switches. This command, IP verify reverse path, then interface name. That's the command in most Cisco switches for routers and switches for verifying that the IP being reported is actually coming from that IP. Zero trust, tight ACLs, controlling how information funnels into your analysis tools, critical. If you leave it open, it's going to be a problem. When you're collecting information, you want to tag it with as much information as you can. What port it came in on, was there a certificate involved, was it transport? All of those things are really important when you need to filter out poison data, which we'll look at in a little bit. And then honeypots are a great catch-all, whether you're doing deception technology. TrapX makes a good one as well, but honeypots shouldn't be there. So nothing should be talking to it. So in the case of where you have poison data, honeypots sort of become your last line to know where the attacker is. Whatever's talking to this non-existent box is a bad guy. The false positive rates on honeypots are very low and they're very difficult to poison. So the attacks we're going to talk about now are basically the entire kill chain minus initial access. You have to have some access to the network for this stuff to work. This isn't an exploit to get you into the network. These exploits or tactics are to break detection once you're in there. So this concept is really critical, whether you're a red teamer or just a bad guy, I guess. The pump and dump technology, or a tactic rather, is about generating attack telemetry from as many unique MAC addresses and IP addresses as possible. And the reason this is important is if they figure out that poison data is coming from a specific IP address, the investigators can filter out that IP address. But if you generated the traffic from 100 different addresses, that's 100 different filters that they have to detect and implement to get the poison out. So best thing is to do this pump and dump. Very simple. Use a VM or a Docker container, Kubernetes, whatever you want to use. Manually set the MAC address, let it spin up, grab the DHCP lease, which gives us a new IP address. Say perform attack, not attach, perform attack, where whatever you're going to do, a SIM scan or any of these other things we're going to talk about. IP config release, right? And then kill that box, spin up a new one with a new MAC, and repeat. So you're generating as many fake source IP addresses as possible, as many fake MAC addresses. So then even when you're talking about doing layer 2 type of response, you can't do it. Favorite way to do this is in Docker. So Docker create, the network I want to use is connected to the NIC of your machine that's running Docker. Set the MAC address. Tell it what Docker image to use. I named it Kali1. I start Kali1. I do stuff, kill it, repeat, new MAC, gets a new IP address. Again, just making it difficult for them to figure out which IP address to come after. Okay, pocket dimension. Wish I had a good diagram for this. Apologize for not having it. But the whole idea here is spin up as many fake containers as you want in a Docker network, and they don't have to be inside the network. So they can be an external 4.2.2.2 and 10. Whatever, 192, and whatever addresses you want. You can create any fake IP address in that container, in that Docker container, so that you have a fake internet. And I call it a pocket dimension because what I can do there is I can create a behavior that says I'm connecting to Office 365's IP addresses, even though I'm not. I'm connecting to a fake IP address because the route is happening inside of this Docker network, this lab network. And then at that point, I can generate telemetry out of that pocket dimension that will tell different stories. And so the way this works, you create a new network. I call it bridge, or it is a bridge, and then give it the internet as its IP space. And then you can create, here I created one container with 4.2.3.1, oh, and 10.10.10.1. And anything that I'm doing between these boxes, it looks like it's happening. Now, it looks like it's happening on this bridge network. And if this bridge network is connected to an access switch that is configured to generate NetFlow, it will generate NetFlow saying that 10.10.10.1 communicated with 4.2.3.1 in whatever way I communicated with it. And so now you have the actual architect infrastructure, network infrastructure, generating records about things that look like they did happen, but they didn't happen in the context of the real world. They happened in the context of the pocket dimension. So a lot of things, can happen there inside of Docker. Whether you're, we'll talk about some more of that later. Now, log spoofing is the most direct way, instant gratification on confusing analysis tools. The hard part is finding it. Who do we lie to? Where do we send the lie? So there's a few approaches. First, DNS. I would highly recommend not naming your log server log.acme.com or sim.acme.com or NBAD or UEBA or Splunk or Witfu or whatever. Don't name them those. Makes it really easy. You can go in with a dictionary of things someone may have named it. Then you're doing NS lookups to find an IP address that resolves to one of those names. If you have a compromised machine that's logging, which every machine should be logging, Netstat will tell you who it's connecting to on Syslog. So that's another approach. And you've always got our good old friend Nmap to do a TCP send scan to look for 514. There's virtually no tools out there that aren't receiving Syslog on 514 UDP and TCP. So you can do that. Of course, it's noisy. So if you're going to do that, make sure you do a pump and dump because they're going to catch you if you're any good. But once you find it, you're going to send the artificial records, do the pump and dump, and move on. And of course, the other thing to note is if you're doing UDP, you can do header masking. So I want to go over this specific, very simple, low-brow way of getting a lie into a system. So this is just using Netcat. So here we're echoing this message over Netcat to a server, and I'll show you the pastebin. The first link I posted in chat is right here, and there's 4 messages that I'm using in this bash script. First, I just create some timestamps because different log formats use different date formats. So I generate those I'm going to need. I set the destination where I'm going to send it. In this case, I'm sending it to port 514. This is a Symantec endpoint protection message. So I just put the variable stuff into this, who I want the attacker to be, and then I ship it, have an ASA message, does the same thing, a FireEye message, and a TrapX message. And then what I'm doing here in this script is I want to spoof as many fake IP addresses as possible because I'm basically going to do things that will trigger these types of alerts. So I want it to look like everybody's doing the thing I'm doing, so that this is a mass implication attack. But again, just using Netcat, use a couple of switches. These might change. This -W is really important for Debian and Ubuntu kernel, but you can play around with that. But this is basically going to send for 10 seconds. The script that I ran at the beginning of our talk, of our time together here, so I sent 47,000 messages to 2 different destinations that spoofed almost 12,000 IP addresses. So I'm one IP address, there's another 12,000 out there. So then when we go back to start looking at the logs, so I sent some to Splunk and sent some to UDP Precinct. And so if I go in and I just say, give me, give it an actual search criteria here in Splunk, show me everything for the last hour. This will pull back those fake records. And, there's in Splunk, you're going to build different layers of analytics, but you can see here's the time where I shot the messages over. You can see all of these different IP addresses, breakdowns of those messages. How many, you see the source is more than 100. So there's, in our case, we did 11,000 unique hosts. So this is a lot of poison data, 41,000 poison messages. If, search here. If we look at that same stuff in Precinct, okay, so pulling back these records in this mess, you can't even see this graph here, but because it's so many. But if you look here, my real IP address is one of these. And the rest of these are fake because I spoofed them all. So my attack is sort of hidden here. And even more, if you go into UBA kind of stuff, this is what, again, the incident looks like. This might not even have my IP address in here, but here's a user credential that I'm spoofing, the different places I'm attacking. Here's 207 different alarms from the ASA. We've got TrapX, we've got Symantec, we've got all these things happening, which is these fake messages. And again, this is the mass implication, that how do the investigators respond if they can't figure out which one of these is really me? When we do look at these records, that wasn't what I wanted, but it'll work, I guess. We can see from the source host, the sending host, sender host, that it all came from the same IP address. And if I look at that even more simply in Splunk, you can see the port it came in on and then the host. So if I filter out that IP address, all that poison data is gone. So this is why if we did a pump and dump and used 100 different addresses, I would have to do this filter over and over and over again for each one of the IP addresses that I picked up on the pump and dump. So yeah, so the two had Christian. It was Splunk Enterprise was one, and then UDP Precinct. WITFOO. So that's Netcat. All right. Now this is a cool thing. If you haven't played with Samplicator, it's been around for a long time on GitHub. I'm not associated with the project, but I do love it. Essentially, what Samplicate does is you say, I'm going to listen on whatever address, 10.10.10.10 in this case, on port 514. So it's going to receive syslog messages. And then you give it a list of destinations to send those messages to. So the reason this is important, let's say we know what subnet the SIMs are on, or the NBAD or the UBA tools are on, but we don't know where it is. And we don't want to do a scan. What we can do is just like list all 254 addresses here, send the message into Samplicator, and then Samplicator will send it out to each one of those destinations. So it'll hit something is the idea there, as long as the ACLs aren't in place. So it's a great way of getting messages to a lot of destinations, particularly if you don't know the correct one. So great project, only runs in Linux kernels, but check that out if you haven't looked at it. And also, just as a secondary note, for those that are setting up logging architecture, Samplicator is a great way when you need to get some logs into to different tools. I want to send some of these logs over to Splunk, some to Witfu, some to QRadar, some to What's Up Gold, whatever you want to do. It's a great tool for working through that. TLS, it's a little bit harder than Netcat, but really not that hard. So this is some Python code. This also works for TCP if you take the SSL context out. But it's just essentially creating a socket. Then the rest of this is exactly the same stuff as the Netcat, whatever message you want to send. And I will say, a lot of my team spends most of their days researching what message is what. There's a ton of this stuff documented, so you can go and Google what's the format, in this case, of semantic endpoint, and just look at the format, swap the variable data out what you want with what you want, and ship it out. So, but you can ship the TLS. Now, obviously, this only works if the server isn't doing client certificate validation. That's why PKI is really important, because that would shut this down, because the server would reject the socket unless you were able to generate a certificate, so have a private key to do that. nProbe is another cool project. Check that out at ntop.org. The way it works, very simple. Run nProbe, point it to ETH0. The interface I'm going to sniff is ETH0, and I'm going to send it to some IP address. So this is great for generating NetFlow records. There's other stuff you can configure here. But where this is really cool is, let's say you have a pocket dimension and the switch isn't going to generate the NetFlow, so you got to generate your own NetFlow. You can create this whole fake pocket dimension with whatever scenario that you want to see, and then have nProbe sniffing the Docker NIC, and then generating NetFlow records about it and sending it out. And so really cool tactic for making your own NetFlow records, and it's really difficult to discern which NetFlow source is the right one and which one's not. And the way that these tools work in flow analytics and NBAD is they have to deduplicate NetFlow records. NetFlow records are unidirectional, meaning they have half the conversation and another set of records have the return server-client communication. So they really all get sort of stitched together and mulched together. So you're able to poison that really easily with nProbe. So a couple of things we'll talk about using that in a bit. API stuff. This is a command to post data into Elasticsearch, as an example. -K on curl. So curl is your friend, just like Netcat was your friend with UDP. -K that says ignore the certificate, the server certificate. Post to whatever endpoint you need to post to. -D is the data. And then here I'm posting a JSON object, which is what Elastic likes. So got that. So NBAD mass implication is sort of what we just did. But what you can also do is build a pocket dimension, and in the pocket dimension, you can have everything scanning everything. And then whether you're doing nProbe to send the NetFlow out, or it's bridged to an access switch, you can have the switch send it. But what it looks like then is when everything is scanning everything, you can't research anything, as we were seeing earlier in the other mass implication attack. But it's a great way if you want to do recon and you want to do a send scan of everything and you don't want them to catch you. One approach is let them catch you, but that they got to find you in the other 100,000 other hosts you just generated doing the same thing. Which one is you, so they can't even track you down. So that's one approach to covering your tracks. It's just make everybody else guilty so they can't find you. The other one is NetFlow masking. So to be invisible, the way network tools work in detecting scans, particularly TCP send scans, is they look for a send packet. So host A to host B, there was a send, no send ACK came back. Host B, send went, no send ACK came back. And so when you start seeing these ratios of send to send ACK skewing, you're going to flag it for a recon. So let's say we do a send scan and we hit the host, send packet goes out, send ACK does not come back. Why not generate a record that said a send ACK did come back? So you can do that through the pocket dimension or through other tools. So great way of covering your masking your tracks all together there. Now, this is definitely a baller, advanced, elite kind of move here. And I'm going to prefix this. If there are red team guys on here, please do not, okay, be very careful if you're going to do this, because baselines take a long time to build. So if you use these approaches in a pen test, the blue team is potentially going to be left with broken baselines for a very long period of time. So I can't give a big enough disclaimer on that. So if you're going to have backups, have a restore plan for getting the old baselines back in. But essentially the approach here is, let's generate traffic that will start pushing the baselines further and further and further towards infinity. So a 5% daily bump is generally enough just to gradually move the baselines without triggering an anomaly alarm. So an example might be, say the baseline is wireless network to data center. So we just generate a couple of packets each day that show a few megs of data moved, and then a little bit more the next day, and a little bit more the next day, and a little bit more the next day. And so you can do that really in every scenario, whether you're talking, whatever you're baselining, if it's data staging, whether it's data exfiltration, whether it's time of day, you slowly move people from, instead of logging on at 9, or if they log on at 8:58, that's a little bit earlier, but not early enough to trigger the alarm. And so if you just start moving those login events, generating a Syslog message of authentication, really simple, do that with Netcat, you're able to push the baseline to where everybody's logging in all the time from everywhere into everything as you start moving those baselines around. So obviously it takes a long time. You can't do that overnight, but devastating to any machine learning model. It devastates supervised, unsupervised models. It's a boiling the frog type of approach to boiling the baseline. Non-repudiation, just to review this one more time, please, where you can get client authentication on TLS, please do it. please do it if you can do it. It does mean budgets are going to need to take this into account, that we need to protect chain of custody, authentication, non-repudiation with our records. IP spoofing, easy, that's a low cost one, right? Just make sure the person doing it knows what they're doing. Building around zero trust, controlling the network flows of data into your analysis platforms, strong ACLs, strong segmentation, honeypots as the catch-all, and then as many ways of doing chain of custody, whether it's certificates that are going into the records, the source IP addresses, what port you received it on, the path it took, all of those things are really important. Last thing to talk about here, and then leave the rest for any questions you may have. A lot of the research that I work on with our team is around comprehension or conversations. There's an open source project. I'm releasing the code at DEF CON this year. It's an Apache 2 project, but essentially what it allows you to do, it's at logfibber.com, to sort of automate a lot of these things. You create the stories you want to tell, you create the things that you want to emulate, the firewalls. You all want to have an ASA firewall and a CrowdStrike Falcon, EDR, and all these different fake things that load what we call reframes. A lot of my research is around natural language processing using a thing called semantic framing, which is basically fully comprehending what every message means. Well, the opposite of a frame, I'm calling a reframe. So it's basically taking a standardized language and converting it into a proprietary format. So it's sort of one of the harder parts of, what I just showed you all, is you have to understand, how does an ASA send a message differently than Palo Alto or Checkpoint or so forth. So the reframes are in the library, they'll be available, but keep an eye out on this, and then targets are just the places to send it. So with that, I'll take any questions you guys have. I've got about 15 minutes left for anything comes up. See, yeah, no sweat on Docker. Docker is really powerful, particularly when you're doing research. It's a great way to experiment, drop off the network, emulate all kinds of real world scenarios in a fake world, and really data poise things about that. Yeah. Christian, research for me, the short of my story is, when I left, when 9/11 happened, I was a Navy aviation electronics technician. I fixed F-18s, and that was a very mature craft. We had pubs that told me exactly how to do the work. We had people, I was trained. There was QA. There was metrics on all those pieces. Transfer out. Have to figure out how to help the Navy do network security or cybersecurity, and we had no pubs. And so the mission that we set out to do here for the last 5 years at WITFU is how do we mature the craft of cybersecurity operations. And the basic thesis is we've built on IT where we should be building on law enforcement models. And there's 7 conversations that I research. The first one is investigators don't understand the data that their tools are providing. The second one is the managers of the investigators aren't able to meter the effectiveness of the investigators. How many units of work should each investigator do? What tools do they need? What training do they need? Third thing, security practices can't communicate with the broader business. So trying to make all of the board members CISSP or equivalent doesn't work. The security practice needs to learn how to speak business. We need to convert data into profit and loss statements. Fourth thing is vendors lie. So how do we hold accountable the people that we're entrusting to do network monitoring, antivirus, zero trust? How can we turn that into business metrics and hold them accountable and not actually just have a healthy relationship between organizations and vendors? Fifth problem is organizations can't share information without inducing risk. So how do you safely tell your neighbors that bad things are happening in a way that's useful to the neighbors without creating a lot of work or creating a lot of risk? Sixth problem, law enforcement and private organizations aren't able to communicate well with each other. So how do I call the cops? How do I inform law enforcement that bad things are happening? And there's some broken pieces on both sides of that we have to research. And the seventh piece is just law enforcement needs evidence to put cyber criminals behind bars. So those 7 areas are what we research. And so it's just looking at on the craft side. And there's also pieces around natural language processing. How do we comprehend all these different types of messages? Data, big data problems. How do I ingest terabytes or petabytes of data each day and make sense of it and federate those use cases? But yeah, no kidding about 2 pots of coffee. I've been chained to this desk doing research with the team for the better part of 6 years now, so don't get a lot of walking around time. Any other questions before we wrap it up? I do appreciate the time and hope to see you guys next year in Virginia. It'll be great to start socializing. I'm hitting the road tomorrow for first in-person conference in Myrtle Beach out at the forensics conference, giving the same talk, so I'm going it on stage. But if anybody has any questions, hit me up, charles@witfu.com. I'm at Charles Herring on Twitter. Find me on LinkedIn. But I do appreciate the time. You guys let me know if I can be any help to you. Back to you, Brian.
All right, that lens cap is a powerful thing. Let me turn that up there. Everyone, thank you for attending. This has actually been probably one of the most interesting talks I've been to this today. I want to remind you of some of our housekeeping items. There is an open invite happy hour for those with the BSidesNoVA ticket at Punch Bowl in Arlington tonight. That's from 6 to 9 p.m. at 4238 Wilson Boulevard in Arlington. On that note, if no one has any further questions, thank you, Charles, and we'll be seeing you.